So the second tool we provide is a link budget. And here again, the link budget, the way we've been providing that is an application. It's an interactive application. And it's a generic one. You can define an uplink from one ground station to one satellite. You could define an inter-satellite link from this satellite to another satellite, and then a downlink. So we've got these ground station link satellites. And the goal here for us is to provide an interface where you will be able to specify, where is my ground station, where is my satellite. It will compute the distance, the elevation under which I can see my satellite, and so on. So you will be able to fill all the details about your communication. You will be able to customize if you want to create, if you've got something special that we have not been taken into account. You can say, oh no, I've got these additional losses, or I want to take some margin, or whatever. You will be able to customize it on your own. And then we will compute the different links, and then you will be able to visualize the operating point. So giving you a quick information on how well you are. Are you able to establish the link with the specific throughput at the specified EB over N0 and these kind of things. For now, it's static, of course, because of the very big focus on low altitude orbits these days. We are looking into the capability to make it dynamic and see exactly, what your invisibility, how is it going to degrade? Do I need to change my mod code? Do I need to do something, to do some handovers and things like that? So the dynamism, the ability to make it dynamic is something we are working on. As all of our scripts, all of our application today, you can export the script. So this is also a very easy way to automate even further. So start with an interactive application, export a script, and then run in a loop. Use with the optimization toolbox we've been providing an example in 24A that show how to start with this, export a script, and then define an objective function and run an optimization algorithm to find the best operating point. Another very important thing is including the propagation model. And so here, especially for geosatellites, we have the ability to compute the availability and use the P618, the ITU P618 propagation loss model to tell exactly to evaluate this availability based on where you operate. If I'm working in KU band over a very clear sky or in a tropical rainy region, things can be quite different, and I may have to consider these different type of applications. So this is something that is available as well. Waveform generation. Again, just to give you an overview, I've been mentioning DVB-S2. We've been starting with DVB-S2. The goal for us is to make sure that we can provide all the waveforms for TX, for RX, including all the different capabilities so that you can run your simulation easily. So the DVB-S2 are there, GPS is there. Something important, I don't know if some of you may be interested in that, but we hear more and more about optical communication. It used to be very popular for inter-satellite links, but we hear more and more uplink or downlink using optical signals. So we are actively working on that. For now, we've been providing an example that show the high photon efficiency telemetry signal, so according to the CCSDS standard. So this is an area where we are making some progress. If you've got some specific requirements, if you've got some feedback, if you want to learn more, We are very open to discussions because we've received a lot of requests for that. We are actively working on it. So if this is a topic of interest, please let us know. We've been implementing the CCSGS for telemetry and telecommand. So I just wanted to be exhaustive here. I'm not going to go into the details, except if you've got some questions. But what I'm going to do instead is show you, again, this is the trend we are trying to do to provide applications, interactive application as much as we can, for two reasons. Avoid to write scripts to do repetitive tasks or things, quick test, and also get started with the tools. So here I'm going to open something that is called an application that is called the wireless waveform generator. If I can find it, it's here, wireless waveform generator. So it's gonna open probably on the other screen. Yes, it's here. Let me move it to the main screen. So the wireless waveform generator is, again, interactive application that will allow you to define the waveform you want to generate. And if you've got some specific toolboxes like the WLAN toolbox, the 5G toolbox, the LTE toolbox, or the satellite communication toolbox, it will allow you to generate waveforms just by specifying just point and click. So the input stream format here for DVB-S2, this is a little bit legacy, but what type of FEC? Is it a normal? Is it a short? What is the mode code you want to use? What is the filter? Where do you want the source to come from? You can define your own function here. And then add some impairments. What if I've got some frequency offset? What if I've got some phase noise, and so on and so forth? So the goal here is to implement this type of features to generate. So here I just need to download the LDPC codes. It's not built in, but it's just going to take a few seconds to download and use the definition of the LDPC matrices. And here it tells me I've been doing something wrong. So I'm going to leave it in normal FEC. Okay, just to show what happens. So here we just showed the constellation. We showed the spectrum. Well, nothing crazy. But what is interesting is that you can add impairments. So let's add just an impairment for the fun. Frequency offset. So that we're going to see that the signal is going to rotate. So now we've got something, we've got a waveform I could feed to my receiver to check if it's still capable of synchronizing. But most importantly, we can export. We can export a MATLAB script. And here it tells me, okay, my waveform generator is a DVB-S2 waveform generator. So this is a function that is provided by satellite communication toolbox. I define the parameters for my DVB-S2. I define a PN sequence as my input. And then based on the stream format, I'm going to use different sync bits. So here it's TS, the GS is probably here. But basically it tells me exactly how to replicate what has been done interactively in my application. So then I can import that and run additional things. So it's also an easy way to get started with the tools. Wireless, okay, waveform generation. So I'll get back to that at the end. I'm going to make some progress now, but I'll get back to waveform generation, especially when we're going to talk about the ability to generate embedded code. Of course, with MATLAB, one of the first things you probably want to do is to establish an end-to-end simulation. So basically, TX, the channel, the RX, with all the synchronization potentially, and see how well it works. So here, to do so, we provide propagation losses, channel models. So different channel models such as the ration channel. This one is the LUTs, land mobile, the LMS. So to mimic what happens when we are actually communicating. I'm not going to talk about the deep space optical for now, but basically this is also something that is provided with the satellite communication toolbox, is receivers that correct for phase noise, carrier frequency offset, and from the Doppler, sampling clock offset. So basically, as I mentioned at the beginning, a receiver that is working out of the box that can compensate and synchronize the receiving data so that you can demodulate the signal. So this is a baseline to get started. So you can get started with something that works end-to-end. Same thing for all the standards. I'm not going to spend too much time on that, but reference applications so that you can get started if you're focusing on CCSDS, if you're focusing on telemetry, or if you want to make some modification to an existing, you always can compare to a baseline and see how it's implemented. Again, it may not be state of the art, but it's something that is working immediately. I will get back to this in a moment. As I said, our goal is not only to do simulation, but it's also to help you go to production. So run on a software-defined radio for rapid prototyping, potentially, but also generate code that you could implement in an actual equipment. I will get back to that. Topic of the moment, 5G NTN. So as I said at the very beginning, we provide a 5G toolbox. We provide a satellite communication toolbox. So of course, one of the things we want to make sure is that these two work together so that we can model 5G NTN. And we already provide examples in the satellite communication toolbox for 5G NTN, especially this one. It's the analyzing NTN PDSCH throughput. Here we implement different channel, the NTN narrowband and NTN TDL. What we do in this example is of course, we pay attention to the Doppler, and here we see how to pre-compensate, for the Doppler because of the satellite movement. The satellite, we know exactly how it's going to move. The orbit, we can tell exactly what it's going to be, and so we can anticipate this Doppler. So this is one of the techniques we've been evaluating and just providing an end-to-end example. See if it could be used. In our end-to-end example, as I said, we model the TX, so we also want to be able to model some basic component impairments with MATLAB. Of course, if you want to implement the complete RF front-end, we've got additional tool, as I said at the beginning, which is called RF block set, where we can model all the components. But I'm not going to address this in details in this presentation. And so here, just this high-level graph in our NTN example, we use these blocks from 5G toolbox. These blocks are just modeling power amplifier, Doppler precompensation. So this is part of communication toolbox. We model the fading channel. So this is in satellite communication, and then we've got the whole receiver with the joint timing and frequency estimation and synchronization, Doppler compensation that we had to add here at the receiver, and then we decode the blocks and we compare, okay, how many bits are in error and what is the maximum throughput I can achieve. We've got probably like 15-20 minutes to go. Do you have any questions on the satellite communication toolbox? Is there something you would like to spend a few more minutes looking into? Do you want to see dedicated examples? Or is it fine like this? No?
There's
no
also a question about the CCSDS. Can you check it, or I can also read it for you if you cannot?
No, I can check it it's in the chat?
Yes, in the at the question section.
In Q&A, okay. Very good question. Yeah, we as usual, we start with the physical layer. But yeah, using the PLOP2 procedures, I have not heard about anything going into this direction, but I can ask the question. And what I'm going to do for sure is make sure that we track this question in our system. Yeah, most of the time we really focus on the physical layer and not necessarily on higher layer. Things have started to change because we now provide some tools to do network modeling, but mainly for Bluetooth because it's in the stack itself, WLAN, 5G, and we are looking into TDMA right now. So I cannot really answer this question. No, I don't think I've not heard about anything where we would be developing this. But if this is something you need, or if you want to have a more focused discussion, yeah, I'll get back to you in any case, and I will ask the question. I don't have the final answer for now, but this is something I can ask. We've been, yeah, the way we operate in general may not be true at all times, but we start from the bottom up. So we start with the physical layer. Once we've got a physical layer that is complete or almost complete, sometimes it's difficult to be 100% complete, especially when the standards are evolving often. Then we go one step above. So here I have not heard about anything in R&D, but I will definitely ask the question. And just to highlight that very briefly, I don't want to spend too much time. But if I go here, just to make sure you understand what I'm talking about. If we look into WLAN, for instance, WLAN toolbox. So now if you look at the way we, WLAN or 5G, we've got the same thing. We've got signal transmission, signal reception. So this is really the physical layer, procedures and channels and so on. End-to-end simulations, that's what we've been looking at. And now we also have this system level simulation where we can define, we've got this wireless network simulator, which is available as a support package that you can download for free, actually. And where we will be able to define a network at specific nodes, define the node, what kind of node is it, what are its capabilities, define some traffic, be able to say, okay, I'm generating on-off traffic video conference so I can adjust my quality of services. And we will provide dedicated examples that show how to estimate the capabilities, not at the link-to-link level, but at the system level. So this is something that is we've got a team dedicated working on that. Again, focusing on WLAN, 5G, and something a bit more generic, which is TDMA for mostly for aero defense users. But this is something we're addressing. We do not have these procedures in CCSDS at the time. I will ask the question.